So problem 3's exercise is to look at again the reaction of bromine water to these alkenes. So the first one is this cyclic system of the action of bromine. So we again believe that the bromine should have an induced dipole moment delta positive to delta negative, and that sets it up to attack from the alkene system the p orbital character of the alkenes to move the electrons nucleophilically towards the delta positive bromine, and we break this bond. So we then have our intermediate, as we can draw, where we have the bromine and a carbocation being formed. So if we were to put the bromine here, this gives us this tertiary carbocation, but again the bromine lone pair delivers for us this bromonium carbocation, so we'll draw this in this manner. So we have a bromonium carbocation, and then we have a majority of water then as the solvent. So we have the water, which could be nucleophilic, attacking from the bottom of this bromo carbocation, or the bromonium ion. So we have water that can attack from the bottom, so we can attack from this carbon, this carbon, so we can attack here and deliver maybe this as the product. So we'll say this is carbon A, this is carbon B, so via carbon A so let's consider the stereochemistry of this. So we have the water attacking from the bottom, so we'll put this as a dashed line as the OH2, and then at the top the wedge bond would be the isopropyl group, and if we were to break this bond here, we have the bromine as the wedge, and then this would be the rest of the molecule in place at this point. So this would give us a final product shown. If we then believe that we can have equally likely attack towards carbon B, but if we consider carbon B here to be a carbocation, this would be a secondary carbocation, less stable than this carbocation. So in terms of energy, then you might say this is the more favourable carbocation, so nucleophilic attack by the water to this mass carbocation here is more favourable energetically. But in terms of steric hindrance, then maybe that there's equally as likely a chance that the incoming nucleophilic water can attack carbon B. So let's suggest we go via carbon B at this route, and we would give a product at this point where we would open up with a bromine at this side. The isopropyl group sits down because the water is attacking from the bottom side of the ring system, and then we have that as our intermediates, that's the positive oxygen, and we would deliver that in place. We would deliver this as our final product. So let's just consider again, we'll just pick one out for the moment. We'll pick route A out. Why would we be attacking from the bottom of the system? So let's just look at this and say for route A by carbon A, if we were to draw this system in place now, where we were to represent the kind of hexagon ring system in this manner, so let's make this the bromonium species. So let's make this carbon A, carbon B, so we'll go C and D, so that's the nitrogen, and then here we would have the isopropyl group in place. Why again would we attack from the bottom of the ring system? So if the carbon A now is the antibonding orbital in place, so this is the antibonding orbital, and we were to attack this orbital from the bottom, we then break the bromine that way. What's our steric product? We would have that, which obviously, hopefully, is equivalent to that species. So, what's our two products in this reaction? This is one product, and this is the second product as well. So we have these two products indicated as the first set of products for this chemical transformation. So let's look at problem 3. Again, the second part is the reaction of this cycloheptene system again with bromine and water. So what have we got at this point? So let's draw this actually out now, where we can show the cyclohexene ring system. Oh, sorry, not cyclohexene, cycloheptene ring system in place. So we'll draw the double bond in place, and then we'll put 2 other carbon atoms, another 2, and then the apex here to be our heptagon ring system as we see. Right, so again, reaction with bromine, so we'll put the orbitals in at this point, so we'll use a different pen, put the p orbital density in here. Reaction of bromine, so we'll take Br to Br, and we'll induce a delta positive, delta negative in this bond. The nucleophilic alkene system attacks the antibonding orbital of this bromine, and we break this bromine to bromine bond at this position, and we form first of all this. So we have the p orbital with the positive charge in towards the bromine. Lone pair of electrons then close back in towards this p orbital, so we form, and again, the bromonium ion. So I'll just carefully make sure I can consistently draw a heptagon ring series. Our bromonium ion is shown, and then we have again reaction of problem 3. We have water molecules, so we have nucleophilic water, and this is to attack the antibonding orbitals. Say this is sigma star, the antibonding orbital of the carbon, so we can either have carbon A or carbon B, and attack in that manner, and this would deliver, so we'll say bicarbon A delivers this system. So that's one isomer form of the system, and then again, if we attack via carbon B, so we'll say via carbon A, we'll point this at A and this is out at B, so we'll say via carbon B is the nucleophilic attack. Again, attack the antibonding orbital lobe here. we would have these two systems as our products. Again, we need to consider whether these are isomers of each other, whether they are mesoforms or distereoisomers, or maybe not any form of stereoisomers, but this will be addressed in another tutorial exercise.